Hello everyone, and welcome to session 2 of the laboratory and data analysis using latent variables and structural equations. In session 2, which was held in person on December 10th, we're going to spend our time talking exclusively about Mplus Example 6.1, which is an example of linear growth using a structural equation modeling framework. The agenda called for a review of what we did in session 1, where we briefly covered the example 6.1. We'll run the code without using shorthand notation. We will not be doing the SAS-proc mix example. We'll save that for a later example, but we will talk quite a bit about constraints using Mplus and what you need to do to mimic SAS-proc mixed output. We also will not be getting to covariates and multiple group analysis today. We'll save that for another session. So, let's run Mplus. And let us call up example 6.1. Everybody should have this or download the file from the Dropbox site. And here we have the Mplus input file for example 6.1. This input file will run one analysis. It is going to be a linear growth curve model. All Mplus input files run only one analysis at a time. The Mplus input file is where we give the commands to Mplus to run the analysis. The command structure for the file includes some commonly used commands, which here are shown as title, data, variable, model, and output. There are other commands, and we shall see some of them in future sessions. The title block can be as long as you would like. It does not need to be terminated by anything like a semicolon as in other commands. This is a great place to keep track of information about the models you're running, like final model 2 or super final model 2, things like that. Helpful notes to yourself. Here we're just reminding ourselves that this is example 6.1 from the Mplus Users Guide and an example of linear growth. The next command is the data command. In the data command, we are telling Mplus information about the data that we're going to use. Here, we're telling Mplus that there's a file, and the file name is EX0601.CSV. Because we don't have any path information here, we know that the file that holds the data, the CSV file, and the input file are in the same folder. Incidentally, we say file equals here. We could say file is, or we could say file are. All will work correctly. That part of grammar Mplus does not care about. The next command is the variable command. In the variable command, we tell Mplus information about the variables that are in this data set. And here we're telling it Mplus that we have 4 variables called y11, y12, y13, and y14. We do it using an array or a range of variables, and Mplus is smart enough to figure out how to expand this variable list. The next command is the model command. This is where we tell Mplus information about the model that we would like to estimate. This command has a linear growth curve model specified, and it's using so-called shorthand notation. We know it's a shorthand notation because of this vertical bar here, an R sign, or a pipe, whatever you'd like to call it. What this command is saying is, please estimate for me a linear growth curve model with 2 growth factors, I and S, and please use the y1 through y4 as repeated observations, and estimate a linear model for change where the repeated observations are observed at uniform increments. And the so-called time steps here are here 3, 2, 1, and 0. Here's a new command. It's the output command. And here we're asking to see the technical 1 output. We'll walk through the technical 1 output together. So let's go ahead and run this. And here's what we get. First, the input reading terminated normally. We love that. Second, we have information about the model that we're estimating. We've got 500 observations, 4 dependent variables, 2 continuous latent variables. They are I and S. We're doing maximum likelihood estimation. Here we have information that we always love to see. The model estimation terminated normally. Here are some model fit information. We have a chi-square test of the model fit that has a non-significant p-value, and a non-significant p-value is good. And we have CFI statistics and CLI statistics, which range up to 1, where values greater than 0.93 are good. And we have a root mean squared error of approximation, which is another statistic I like to look at, where values less than 0.05 are good, and there's a little reminder here that that's a good value. And here we have the RRMSA is some value less than 0.0004, I guess. All right, so here we have our model results. First, we have the so-called measurement model, where we have our intercept latent variable loading in each one of the dependent variables with a weight of a 1. These are fixed parameters. You know they are fixed parameters because the standard errors are 0 and the estimate over the standard errors are 9999999. This is your clue that these are fixed. Similar with the slope, we have standard errors of 0 and estimate over standard error ratio and p-values of 999. These are also fixed parameters, and here they're fixed. The values that they're fixed at correspond to what we put up in the model statement. Next, we have a covariance parameter between the slope and the intercept latent variable, and here we can see that we have a large covariance relative to its standard error. We could say that it is significant, but sometimes that's frowned upon. Here we have the means for the intercept and the slope factor. So the mean of the intercept, this tells us the expected value given a linear model for these data when slope is 0. So that's here at the baseline. And this mean is 0.0523. And then we have our slope mean. The slope mean is going to be the per time step change in y per unit increase in the slope. So we're saying we gain about 1 point per time interval in our outcome variable. Here we have our intercepts for our y's. They are all estimated at 0, but they're not estimated at all. They are fixed, and we know they're fixed because we have our 999s. And I'll explain more of that when we go into our longhand notation. We have variances for intercept and slope factors. In both cases, estimates of variance that are large relative to their standard errors. So in the olden days, we used to say we have evidence for significant individual differences in the starting value, which is I, and the pace of change over time, which is S. But we don't say that anymore. And here are the residual variances. So these are the variances of the error terms in the regression of y on I and S. And they look pretty constant over time, although maybe a little bit inflated for the last one.